Alright, so now in part 3 of 1.2 basic class of functions, we'll be covering some other types of functions. So let's get started. Okay, so now let's go talk about special kinds of functions called rational functions. So rational functions are functions where one part is divided by another part. So they look like p of x divided by q of x. Alright? P of x can be a constant or a polynomial, and q of x is always a polynomial. Alright? Let me go describe let me go show you some examples of what rational functions are and what rational functions are not. So 2 over x is an example. You have a constant on top and a polynomial on the bottom. 3 plus x divided by x minus 1 is also another rational function. X to the 99th power minus 1 divided by x is also another example of rational function. X minus 1 divided by x cubed minus 1 is also an example of a rational function. Here are examples of what aren't rational functions, so not examples. X divided by 2. The bottom always has to be a polynomial. 2 to the x divided by x. 2 to the x is not a polynomial. X squared minus 5 divided by 3. Again, the bottom in this case is not a polynomial. Sine of x over x. The top again isn't a polynomial. Okay, so now there's a few things that I'd like to talk about regarding rational functions. So remember how I described a rational function as p of x divided by q of x, where p of x is a constant or a polynomial and q of x is definitely a polynomial? Well, if q of x is a polynomial, there's a good chance that q of x equals 0 at some value of x. At that value of x, f of x doesn't exist or is undefined. Because you just simply cannot divide by 0. At such, when x is 0, the function can behave one of two ways. The function f of x can either has an asymptote, a vertical asymptote, or a hole when q of x equals 0. So those are the two things that could happen around that x value when q of x equals 0. It either has a hole, which is when the function behaves completely normally around that x value, or it has an asymptote where the function goes to infinity or to negative infinity as you get closer and closer to that x value where q of x equals 0. There's also one more thing I'd like to talk about, which are horizontal asymptotes. So let's redefine our rational function, which is p of x divided by q of x. If p of x has a degree that is less than or equal to q of x, I'm going to go write that down. If p of x has a degree less than or equal to q of x degree. Alright, so if the degree of p of x is less than or equal to q of x, then f of x has a horizontal asymptote. I'm going to go write that in the next line. If the degree of p of x is greater than q of x, then there is no asymptote or horizontal asymptote. But if it is less than or equal to the degree of q of x, then f(x) has a horizontal asymptote. Okay, so now let's go talk about power and root functions. So power or root are functions that have the following form. f(x) equals kx to the c, or y equals kx to the c, where k and c are just any numbers. They don't have to be integers, they don't have to be positive, or they don't have to be negative. They can be any real numbers. Okay, so power and root functions are actually interconnected. Let's take a look at the function x to the 1/2 power. That can actually be written as square root of x. Would you like to take a guess of how you can rewrite x to the 1/3 as? If you guessed the cube root of x, you're correct. Let's try x to the 1/99th. What do you think that equals? If you guessed the 99th root of x, you're correct. Alright, so if I write f of x equals x to the 5/2, that's the same as x to the 1/2 to the 5th power, and that's also, or x to the 5th to the 1/2 power. Alright, so now you can rewrite that. You can rewrite x to the 5/2 as the square root of x to the 5th power, or x to the 5th, or square root of x to the 5th. So that's how power and root functions are interconnected. One more thing I would like to talk about before moving on to the next slide are negative exponents. So I had previously written that fx equals kx to the c power, where k and c can be any numbers, both positive and negative. So what does it look like if the exponent here is a negative number? So let's say we have a function f of x equals x to the negative first power. That's the same as taking the reciprocal of this and then making the power positive. So x to the negative first power is 1 over x to the first. If you have g of x equals 99x to the negative 88th power, that's just same as 99 divided by x to the 88th power. Alright? So basically, if you have a power function kx to the negative c, you can just rewrite that as k to the xc power. Alright? So that's just how negative exponents work. Alright, so now we're going to go over piecewise functions. So far, all the functions that we've been looking at are just one big piece. However, as you may notice here, this function is broken up into actually not so many, but 3 different parts. And piecewise functions allow us to do that. They allow us to break a function up into multiple different subsections as needed. Whereas regular functions don't give us that freedom to do that. So let's go delve into what piecewise functions are. Let's now learn how piecewise functions are written. So, normally, a function would just be written as fx equals some polynomial. However, that doesn't allow you to break up the function into multiple parts, as you saw there in the previous slide. So how do you notate it? We have a bracket, a curly brace, and then we just write our equation 1, and then our domain 1, equation 2, domain 2, and our equation 3, and domain 3. Domain 1, 2, and 3, they're all going to be written in inequality form. Also, piecewise functions are not limited to only 3 parts. We can have as many parts as we want. I'm just gonna add a bunch of dots here to sort of signify that you can have as much as you want. We can even have like equation 999 and domain 999, and we could still continue adding more as needed. So let's go take a look at a certain piecewise function. Fx equals 2x minus 1 from x is less than 0, x squared when x is greater than equal to 0, less than 5, and just fx equals 5 when x is greater than 5. So this is how we can write a piecewise function. Let's go take a look in the next slide how such a piecewise function would look. So this is the same piecewise function that I had written previously. Alright? So this is the 2x minus 1 graph that goes from that exists when x is less than 0. So I'm just going to divide this portion. This portion from 0 to 5 is just x squared. And then this is just 5 when x is greater than 5. So this is how piecewise functions can be created.